Heat, temperature. You probably use these words all the time, maybe even interchangeably. But do they actually mean the same thing? Spoiler alert, they don't. And we're going to break down exactly why using these awesome handwritten notes as our guide. By the end of this, I promise you'll get it.
All right, let's kick things off with a simple question. Is 0 degrees hot or cold? What do you think? Well, it's kind of a trick question. Before you can even answer that, you have to ask a better question. 0 degrees what? Because as you're about to see, the answer completely depends on the scale we're talking about. So, to get to the bottom of that, we've got to look at how we even measure temperature in the first place. And it turns out there's not just one way to do it. Nope. These notes here lay out 4 different scales. Okay, so check this out. Each one of these scales is kind of anchored to the same 2 things, the freezing and boiling points of water. But man, they all describe it so differently. You've got Celsius, which is super neat, right? 0 for freezing, 100 for boiling. Simple. Then there's Fahrenheit, with its kind of random seeming 32 and 212. Kelvin is the big one for scientists. It starts at the coldest temperature physically possible in the universe, absolute 0. And then you've got this other one, Reaumur, which you don't see as often. It's really like having 4 different rulers, all measuring the same thing, but with totally different numbers on them.
All right, so with all these different ways of measuring, you're probably wondering, how in the world do we translate between them? And yeah, you can't just add or subtract a number. But luckily, these notes point us to this one beautiful universal formula that basically acts as our translator.
And here it is, this one equation. This is the key that unlocks everything. The best way to think about it is like this. Imagine the distance between freezing and boiling on a thermometer. No matter which scale you use, Celsius, Fahrenheit, whatever, a specific temperature will always be at the same proportional spot along that distance. This formula basically captures that constant ratio, and that's what lets us jump from one scale to another so easily. Okay, so now that we have this amazing formula, we can use it to solve a classic little brain teaser. Ready? Is there any temperature where the number you read on a Celsius thermometer is the exact same number you'd read on a Fahrenheit one? I mean, it seems pretty unlikely, right? Given how different their numbers for freezing and boiling are, but the math doesn't lie.
And check out how it's done. The calculation right here in the notes shows us the trick. You just take that big conversion formula and you set the value for Celsius and the value for Fahrenheit to be the exact same thing. You can just call it X. Once you do that, it's just a little bit of algebra, and boom, you can solve for that one magic number where the 2 scales perfectly align. And there it is. The one and only answer, -40. That's it. -40 degrees Celsius is the exact same temperature as -40 degrees Fahrenheit. It's that one single lonely point on the thermometer where these 2 completely different scales meet up and actually agree on something. Pretty wild, huh?
Okay, so we've nailed down how to measure temperature. That's the what. But what about the why? What are the deep down rules that make temperature work the way it does? Well, that brings us to a really fundamental law of physics, and it's all about finding balance, or what scientists call equilibrium.
This idea is called thermal equilibrium. And honestly, it's just the universe's natural tendency to find balance. Think about your morning coffee. You pour cold milk into hot coffee, right? You don't get sips that are super hot and then suddenly ice cold. Of course not. The heat from the coffee flows into the milk until the whole thing settles at one single uniform temperature. That final balanced state, that is thermal equilibrium.
Now, this simple little drawing from the notes, it looks basic, but it's the key to a surprisingly huge idea. So picture 3 things. Let's call them A, B, and C. Now, A and B are separated by a wall that insulates them. Think of it like a perfect thermos. No heat can get through. But both A and B are allowed to touch C through a wall that does let heat pass through. So what do you think happens? The answer is actually the foundation of a major law of physics. This right here, this is the 0th law of thermodynamics. It basically says that if A reaches the same temperature as C and B times also reaches the same temperature as C, then A and B must be the same temperature as each other. It sounds almost obvious, right? Like, duh. But it is so important because it's the very reason thermometers work at all. Think about it. The thermometer is object C. It touches you, your object A, and it reaches your temperature. Then you can take that same thermometer and stick it in your soup, object B, and now you can reliably compare the 2. Without this law, thermometers would be useless.
Okay, which brings us to the main event, the big showdown. We've talked about scales, we've talked about laws, and now we can finally put all the pieces together and tackle the core difference between heat and temperature. Because I'm going to say it one more time. They are not the same thing.
So, let's break it down. Heat is a form of energy. It's the total energy of all the tiny moving molecules inside something. Now get this, a whole bathtub full of lukewarm water actually has way more heat than a tiny little cup of boiling water. Why? Because there are just so many more water molecules moving around in the tub. Temperature, though, is different. It's not the total energy, it's the average energy of those molecules. It's a measure of how fast, on average, they're all vibrating. And here's the absolute key, the thing to remember. Heat is the cause, temperature is the effect. You add heat, the cause, and you see the temperature go up, the effect. So, let's wrap it all up. Heat is the energy. Temperature is the reading on the thermometer. Heat is the why. Temperature is the what happened. It's a simple distinction, but it's absolutely fundamental to, well, pretty much everything. And that leaves us with one last fun little historical puzzle to chew on. If this zeroth law is so basic that it explains why thermometers are even a thing, why on earth isn't it the first law?
Thank you for watching my video. Like, add, subscribe, and hit the bell icon.